All right. So hi everybody. Welcome back. For those who are in Guatemala, like us. And so hope you had a good time with Chuck. Look at the recording, and looks like he did some. He has some great activities for you. So we're gonna keep on going in our short course, and so today we're gonna talk about lava flows, and Einat Lev is gonna lead the session. And so, like I said in my email yesterday, we'll try to do this a bit more interactive, so then you guys could actually, if you guys could actually log in on Victor and have the hub open, so then you can actually follow the activities and do the workflows with us and run the models with us. So then we can compare outputs and things like that. So I think that would be great to do that. I mean, we have several codes for lava flows already available on VHub, so that's one of the volcanic process that is the most available on Victor. I keep using VHub instead of Victor, but that's fine. So it would be good to show you the differences between the codes and talk a bit about that. So don't hesitate, as usual. If you have any questions, use the chat or just raise your hand or just use your mic and speak up. We'd be happy to take any questions and answer them during the session. So Einat, up to you.
Hi everybody. Really great to see everyone. I haven't been at the last few sessions. Was in Guatemala as well, but I hope you are all learning as much as possible. I'm gonna share. Let's see if I can share my whole screen, because that will make it easier to go back and forth between the presentation and the okay, so now you're seeing the Teams screen, right? And now you're seeing the presentation. Okay, so we'll just do that. So yeah, I'm Einat Lev. I'm a research professor at Lamont-Doherty Earth Observatory, which is part of Columbia University. And I study lava flows in the lab and in the field and on the computer. Maybe that's part of why there's so many lava flow codes on Victor. Some of the motivation for Victor, for me, was having a hard time finding and using lava flow codes and thinking that if I had a problem like that, maybe other people had a problem like that, and maybe it's better if we just have a place where everyone can go and it's already set up. So motivation for studying lava flows in general, I'm sure you all know, they cause a lot of damage in places where there's exposure. These are some satellite images from before the 2018 eruption of Kilauea volcano in Hawaii. This is a town or a village called Vacation Land. It was beautiful right by the coast. Here's an old volcanic cone from before, and then that's how it looked after the eruption. So it was obviously a lot of damage. And then this is Leilani Estate, a little bit up the rift, where the fissures really actually opened during that eruption, and that's before and that's after. You can see some of the vents for that eruption here, just in the middle of the state. And this is a geothermal plant, so there was a lot of worry that this big facility would get hit by the lava as well. There was a lot of damage to utilities, so not just private houses and agriculture. So here's that geothermal plant again. Here is an attempt to protect some of the power lines by creating insulations against them. And the lava got really, really close to both. A little bit more recent, the La Palma eruption of Cumbre Vieja, and you can see here a video that shows some of the houses being impacted by that lava flow. The damage from this eruption, combining the explosive and the effusive parts of it, because it was a compound eruption, was more than $1 billion. So it's a major damage, and you can see here how it crossed the roads and impacted the infrastructure. Here's another video from that eruption, and you can see that now we have a lot of data. Before, most of the data that was available, for example, for testing models, was the footprint of a flow, how maybe sometimes how quickly the front advanced. But now with the advance of drones and aerial photography, we can get so much more details, like the surface features and how they evolve and how they interact with structures and buildings and things like that. So there's a wealth of data that's coming into this field of studying lava flows. For example, here we analyzed the flow in the channel using velocimetry and calculated very quickly how fast each part of the flow is moving. These are more examples. So it's easy to do, and now there's data that can be used, for example, for testing models, but also for inputting more complicated rheology structure. We'll mention that a little bit more later. Another famous lava flow eruption recently was the sequence of eruptions now in Iceland and the Reykjanes Peninsula. This is from 2021 in Fagradalsfjall, and since then there's been a few more. There's probably one coming in the next couple of weeks that would hopefully be short, but just a few weeks ago there was a lava flow eruption that was only a day and a half, not a lot of volume, but it was directed exactly the wrong direction, and it cut a major hot water line that cut the heating for residents in the peninsula for a few weeks. So that was a big deal, in Iceland in January. Also in Fagradalsfjall, there was attempts to divert the flows, and that's something that maybe in the planning of diversions like that, where models can be very useful. And you can say, well, how fast, how much longer can I slow the flow down if I put a diversion here or a dam there, and that's something that's important for planning. And you can see still, even though there were dams up here and up there, they got overtopped eventually, but it made it still a little more accessible for a longer period. So when people come to modeling of lava flows, there's a lot of different goals, reasons why people would do that. There's the short-term forecasting, which tries to answer the question of where will this lava go? If I have a vent and I have a volcano or a topography, where would it go and how quickly will it get there? Then there's kind of a longer-term assessment for hazards and planning. Where will some future lava flow go? Where would it erupt from? How much will it come? How much will come out? How hot will it be? What's the density? What's going to be the flux? Things like that. Then we can use models to interpret deposits. So if you go to a place that has a lava flow, that can be subaerial on Earth, but that can also maybe be planetary flows where we see a lava flow that we haven't been there to witness. So a model can help us answer questions like, what was the effusion rate? What was that lava like? What was its viscosity or density? And then models can be used as a kind of a basic science. How does the landscape change, or how does the properties of the magma change, impact the flow, pulsing, and so it's kind of sensitivity to the different input parameters and environments that models can help us. And we can't just go and do an experiment in the field, right? I mean, we can't control any of these things, but a model can allow us to do that. And the question that is relevant to all of these different aspects and uses is, how uncertain are these above assessments? So how accurate are our answers to all of these? Lava flow models are often characterized in two categories. One is called physics-based and one is called rule-based. And that means basically, are we solving differential equations that describe conservations of mass, momentum, and energy? That would be sort of the physics-based code. Or are we propagating the magma in space based on some rule that says, are we did we go beyond a certain threshold length that we know is typical for that volcano, and then we stop? Or are we propagating because this is the steepest path? So it's not solving a physical equation, but it's solving a rule that is often based on intuition or physical observations. Another characterization is deterministic versus probabilistic. Deterministic models answer questions such as where, when, and how a lava would go given input parameters. Probabilistic models answer that as well, but in a probabilistic sense, that like how likely it is to go in certain places. And that kind of categorization is a little bit artificial, in my opinion, because any deterministic model can be run in a probabilistic framework if you have enough sufficient power. So if you have a model that gives you the same result every time because it's deterministic, but you run 5,000 of them, varying the input parameters based on some prior assumptions on your distributions, then it becomes probabilistic and it gives you a probabilistic answer. So these two can be combined. Also, there's so many lava flow models, and you can sort of sort them out based on the complexity of the physics and the numerics that is considered. And I have this kind of like steps that the simplest models, they only take topography and vent location and propagate the lava based on rules. And then a step above that, there's cellular automata or lobes based models that do the same thing with a slightly different numerics. And these kind of two categories of models answer mostly the question of where. If you go a step over in terms of the physics and numerics, then we get to the kind of the physics-based models that can be either depth averaged, one dimension or two-dimensional models, or you can go even beyond that to the fully three-dimensional models. And what these models add is answers to the question of how quickly the lava is going to get to where it's going, because they also involve solving for things like temperature and velocity, while these models do not. So what I'm going to do for the rest of this presentation is go through some examples for these models that we already have on Victor, or that we're in the process of installing on Victor. And we'll go and I'll either demonstrate the notebooks that involve them or ask you to do that. One of the simplest codes that are available for modeling lava flow propagation is called downflow, which goes through these following steps. First step, take a DEM, put a vent somewhere. So for example, this is a shaded relief map of a DEM somewhere in Etna, and we put a vent here. And then for a large number of iteration, modify the elevation at each of the cells by a random value within a range that you provided. So that can be, for a typical kind of Etna size DEM, you'll have a change of delta H of maybe 5 meters. And then once you add that random noise to your DEM, take a steepest descent path from the vent through this new updated DEM. There's an option to go all the way to kind of the end of the DEM or to where the ocean hit, where the lava flow hit the ocean, or you can say only run the flows to 1 kilometer or 5 kilometers or something like that. And then at the end, to summarize the results by looking for each DEM cell in the grid, what was the probability of any of these paths to go through that? So you'll see in this map where the colors show the probability is that there's an area where many paths went through, even with the different iterations of adding noise. So that's all these dark paths. And then there's paths that are less likely to get inundated, only sometimes that predicted flow went through. And in this map on Favale et al.'s paper, you'll see also a white outline, which is actually the outline of an actual lava flow in 2006. And you can see that there is some match, but also some mismatches. Here's another test case for downflow in a more flat topography. So any variations may have more impact. This is 2014-15 eruption of Fogo volcano that was within the caldera. The black line is the outline of the flow, and you can see this is the data, the observations. So this is model, where would more likely there'll be flow going through. So there's a lot of runs went this way. There's fewer runs that went into black areas. This is the actual data. You see the area that got actually a lot of lava thickness, that's the DEM difference map, is an area that was likely to get a lot of flows. So if there's a dip, a lot of your path would go, even if you add some noise to the DEM. So this is the probability, and you see that all this red area that had a high probability are indeed overlapping with the actual flow. The actual flow didn't go that area, even though the model did predict that it would. Same here, same here. So in that case, the model kind of over-predicted the coverage area. And maybe the flow length should have been kept smaller, or they should have changed some other input parameters. Downflow is very fast, and it's often used to produce hazard maps, where the probability of inundation is multiplied by the probability of the vent location. This is a map, again, for Etna, where the vents can go in a lot of different places, and then you want to have probability of inundation in towns around the volcanoes and roads that is considering the vent opening density function as well as the inundation function, that probability that comes from the downflow models. So I'm going to try and go into a browser, so you'll see a downflow notebook. So this is just a regular Jupyter notebook that we just developed, and the different steps that you go through, I'll just walk through. First, we import some of the libraries that are needed, including the Victor library that we need for some of the plotting. And then we provided a DEM and plotted to see that it is indeed the DEM that we wanted. So this is a DEM of a nice cone volcano, Momotombo in Nicaragua, that had a big lava flow that went kind of this way. And then need some parameters for the downflow run. So it's how many simulations, how many paths do you want to go, and how many steps can be done in each of them. And then where would the vent be located? This is just in columns and rows within that DEM grid. What's the maximum length of the flow that I allow? Just said 6 kilometers. What's the resolution of the grid? And then this section writes these parameters into an input file. And then we're just going to run the model. It's already in Python, so I'm just going to call Python and call the downflow.py file. And it would show me some progress bar and run through. Like you see, it's going to be very quick. And then if you're interested while it's running, this is the actual Python code for downflow. Again, we said it's taking all these input parameters that we just provided, and it goes through the grid and the kind of the number of simulations that we said, and then it's adding that random noise to the DM and looks for the paths through that loop there, and then it saves the output as a figure. And then in the notebook, what we do, the next step is load up that figure. And you see we got some, I just put the event kind of like here. Well, in reality, the flow started here, would have been a little bit longer, but it went basically where you would expect it to go. And you see that was super fast, and it's already giving a probability of inundation. So that's downflow. PowerPoint. Any questions so far about the background or the first simple models that we showed?
Can you just show where downflow is located on Victor, so then people can, is there a workflow already there or in the shared folder?
Right. So right now it is in, oops, sorry. It's in shared models downflow.
Okay.
Right. It's not part of the setup script yet because we just added it, but it will be. Also, this notebook is slightly dated. It's from yesterday. Well, I made some changes today already. So we're gonna update that. But it's under.
But they can see the code and an example of a notebook for them.
Yeah, you can see the notebook and you can see the source code itself, downflow, the loops and all that, and a notebook that calls it.
Okay, thanks.
Sure thing. All right. Another code is called multiflow, is somewhat similar. Takes a DEM, put event somewhere, filter the DEM so that they do a little bit of a geomorphology analysis on the DEM itself, and then they disperse lava to not just the steepest descent path, but to multiple cells based on a rule, and then filter that result afterwards. And they do that at different resolutions of the DEMs, so that can do some sort of summing. And then, for example, these are some examples from the original multiflow paper where they looked at Etna and Mauna Loa and Kilauea and were able to show also the intercept between what the model was given, but there's a probability or the influence they call, low versus high influence, and the actual path, that would be those black polygons, the actual coverage of the actual flow, and looking at kind of overestimation and underestimation by the models. We don't have multiflow on Victor yet. The code was in MATLAB, and we're in the process of translation it to open source. This is kind of looking at the sensitivity of multiflow results to DEM filtering. This is no filter, and this is very, very like long length scale filter, wavelength filter. So you'll see here you get a lot of like tiny flows going some places, and here everything kind of goes in the same area. Sorry. The next family of models that I'm going to show is called cellular automata models that have been very popular in volcanology, but also in a lot of different other fields, in the science and in other sciences as well. There's basically rules for transferring lava between cells. So let's say this is my vent, and then I have a rule of where that lava should go. And that rule can be simple, like go to the steepest pass, or it can be a little bit more complicated, such as give 40% to the steepest and then 20 to all the others, or something like that. Or it can be based on the difference in height between what's already there or what's new. And they can be based on temperature. That may be a proxy because we don't have time. We're not solving for time here, but there can be, if I'm this distance from the vent, that means it's probably that much colder. That means it's probably not going to disperse as quickly and as easily. So that the rules can be as simple as complicated as one wants. One code that is popular cellular automata code for lava is called molasses, that Chuck and Laura developed at USF. And here's an animation they show how they disperse from one cell to the other. And this is the lava thickness that is being tracked between the cells. So it started at 3 meters in the center, and then it just gets dispersed and dispersed and dispersed. And what the rule is that there's a cap on what the thickness should be overall and what the overall total should be. So this is an animation that you can go onto that website, Chuck's website, and play with if you wanted to. And you can see, and this is, it started with a flat topography and then built a pile, essentially. So it's higher in the middle and thinner on the perimeter. And it grows and grows because we tell it how much to add in every time step. Input for molasses include a DEM for the region, a location for the vent or vents, can be multiples, the total eruptive volume, the total volume to add in each pulse, and then an average final flow thickness. So let's say I know I want 10 to the 8th cubic meters of total volume, and then I want it to be on average 30 meters everywhere around the floor. And this is how the algorithm goes. You give it a configuration file and initialize, you load the DEM, and then have a pulse in, distribute, go back, pulse, distribute, see if there's any remaining, and then put an output with either an ASCII or DOTIFF files, and then end. So here's some test cases from molasses, looking at the Solbacic 2012-2013 eruption, and comparison again with that the actual flow outline in black. And you can see that overall the models did fairly well. Depending on, these are comparing two different DEMs, Tandem X versus SRTM. They have different spatial resolutions. And then some statistics on what's the false negatives and false positive and true positives in color. Here's running molasses for Fagor-Dasville, which we did on Victor, not on Victor, on Chuck's geoscience community codes website, where they have the Fagor-Dasville topography, and you can put in multiple vent locations because there was a pretty long fissure, and then the lava gets dispersed. Of course, it's very sensitive to whatever parameter you put in. There's only a few, but they matter a lot. So I wanted to try and do an activity now with everybody. So if you can, so you can try molasses on Victor, and I have the instructions here. I'm gonna give it maybe, I don't know, 10 minutes to see how everybody can do that. I'm gonna go back to the screen to see if there's any question. It's hard to know without seeing everybody's faces if you guys are in there. So I'm gonna put the instructions up, and if anybody has any questions, either speak up or put a distress symbol with a emoji, or raise your hand, or put a message in the chat. Sorry, instructions. Are you able to see when people log in and run?
I can't see when they
Not live.
run, but I can see if they're logged in.
Okay. Can you check?
They are. I checked before class. Seems like, yeah, so 7 out of 10 people are doing it, so most people.
Yeah. All right, so the end result should be a figure, and we're gonna set up a Google Doc and share it in the chat that everyone can copy and paste the map that you get at the end, so that we'll see who's getting it.
Okay, I'm getting an error when I run the notebook.
I was waiting for getting the error, people.
Okay.
Yeah, what's happening?
I got Kiro. That's when I run the DM check. I got Kiro, blah, blah, blah. What does it say in the end? No such file or directory for asdf.asc.
Okay. Is the DM, can you provide it a different DM from the DMs folder?
It's in the DMs folder.
It's there?
Yeah, it could be that because I had I actually installed it before, like a year ago. So I don't know if you guys did some changes in it. Let me try to just delete it and set it up again. Oh, it doesn't want to delete that.
I have a fresh copy, so I'm gonna.
Yeah, I think he just has a really old copy.
Yeah.
Because the new versions should be a little bit more
Right.
streamlined.
Okay, I'm gonna rename them.
Could you maybe go over how to like save the plots out of the Jupyter notebook again? I know we talked about it a little bit ago, but I kind of forget how to do that.
Right, so let me go back to mine. And then here's a map. And then if I one way to do it is just do like a screen capture just for quick right now. But Sam, do you remember how to save that plot? Right.
One thing right now, I think is
I mean, there's a plot.savefig command, so you can use that.
you can actually save it as an image if you use shift and right click. It saves it locally.
Wait, I need to run the whole thing before I can actually put it. Wait, what happened to my coordinates?
So if you want to save it on Victor, you'd have to do a save fig. But if you want to save it locally, you can actually just do shift and then right click on the image, and then it'll save it locally.
Right. So you can say to the group, but
Sure.
the one
I
thing
just
that,
don't want to echo back and forth.
yeah. So what I did here is just added a line to the workflow that is plot.savefig in the file name, and now I have a PNG file that I can download to my local computer, and that would, and then I can put it on the Google Doc or whatever, like that. Then,
awesome, thank you.
and I can upload from computer, and then I download this. I'm glad to hear that you got a figure already. Anyone else at that point yet?
Yeah, I'm good.
Excellent.
Just saving the image now.
Excellent.
Yeah, I found out that I had an old folder called Mollasted already, so that was creating the problem.
Yeah.
But I just fixed that now.
Mm-hmm.
Okay, so let me run that again. Okay, yeah, got it here. It looks the same as yours, so is that normal?
Yeah. Good.
Okay.
Yeah, because I mean everyone is doing with the same parameters, so hopefully all the maps will be identical.
Okay.
Right. I mean, if you go ahead and change your DEM or change your parameter.
Yeah, we'll change an input parameter. That would be good.
Yeah. Just wanted to get everyone at the same spot to see that everybody's getting the same.
Yeah.
Oh, please, could you give permission to edit, because we
I
cannot.
I just added. I just changed the permissions so everyone can add figures. So hopefully you will. Great. Everybody got maps. Super cool. All right. So let's go back to presentation and continue talking about other models that we have.
Oh, somebody is asking if you can show again how to generate the PNG file.
Yes. So what
maybe
I did was
just copy and paste the line that we need to add on the chat.
Yeah. So what I did, I don't know why it's not showing so well. Here, I added this line here, plt.savefig, and then the file name.
Can you copy that in the chat, please?
Yep.
Yeah, thank you.
I'm gonna do that. It's not with the multiple windows. Excellent. All right. Anybody need more time, or are we good? All right. So that's molasses, and it's on Victor, and it's readily available, and you guys can go and change input parameters and change DMs and run it, and you see it running. It runs very quickly, like we said, because it's very, very simple. Another popular cellular automata code is called QLava with an H. And what's interesting about it is that it's a QGIS plugin. So you'd have to go into the graphical on the GUI part desktop that we have on Victor and run QGIS there. And then we are in the process of getting the plugin installed in the Victor distribution, so then you'll be able to run it. Or you can go ahead and download the plugin from the QLava website yourself and do it kind of locally in your own account. QLava has a dispersal probability for the different cells that depend on either the difference in height between the two cells or the difference in height and squared. And they have some mechanism inside to overcome small pits. That is this kind of if conditions here in small font. And then they have sort of an artificial cooling that have a reduced probability for dispersal as the distance from the vent. So they don't solve for temperature, but they do have this sort of accounted for. And they have multiple ways to limit the flow length. That can be a set number, or it can be calculating through a parallel solver called Flogo that does account for temperature and cooling and crystallization and things like that, and we'll talk about it in a minute. Here are some test cases for QLava from the original Mosu paper for Etna and Nyiragongo. Again, you see a comparison with the footprint of the actual flow, and they did fairly well. This is, in a way, reminding some of the downflow results because it's a steepest descent. It's a combination between steepest descent and cellular automata, but this is kind of a typical QLava result. We are in the process of installing that plugin. I just confirmed with the developer that it should work on Linux, even though the website says Windows and Mac only, but we'll try it. A code that we do have on Victor is Mr. Lavaloba that was popular. It was used by University of Iceland recently for all the Reykjanes eruptions to forecast what they're going to be doing. And it's a rule-based code, but it's not grid-based like the cellular automata code that, like molasses, for example. So the way Mr. Lavaloba works is that first, given a DM and a vent location, you put a lobe somewhere on what the vent is. And then with each step, you determine a lobe, which of the lobes that you are collecting will bud a new one. So there can be a kind of a factor called epsilon, where you'd only bud a new lobe from the youngest. So that would be like the tip of the flow. Or if it's 1, then every existing lobe in the collection can start a new one. So when you have one lobe, of course it doesn't matter, but when you start having multiples, then that parameter tells you which one is going to start dispersing more lava. And then once you know which ones are going to birth new lobes, then you need to figure out which direction. So there's some probability for the direction, and then you so there's a preliminary direction that is set by the steepest descent usually, and then you perturbed it to reflect some local distribution, and you add a little bit more, and then eventually that gives you that kind of orientation of the new lobe, and they all the lobes are can be set to be the same size, or there can be a distribution for that as well. So here are some test cases, kind of sensitivity analysis for Mr. Lava-Loba. In this direction, they are increasing that lobe exponent, which acts effectively to decrease the runout. So if you have EB0, like we said, then it'll only birth new lobes from the very tips. But if it's 1, it can start them everywhere on the flow. This is increasing alpha max, which is that distribution of azimuth. And if it's high, then it's giving you a very narrow flow. If it's low, then it'll give you kind of a more widely dispersed flow. So, and you see that none of them really, like these two parameters may kind of matter a lot for what the resulting flow looks like, but there's not a lot of physics or intuition that goes into that. So what happens is that people want to use this model for their volcano, need to calibrate it on past flows and some kind of intuition, or trying to run different things and see what looks like my flow kind of thing. Here are some more test cases. Kilauea 2014-15, giving thickness, and then Etna 2001, which a lot of model testers use because it's a very narrow flow that is on a very steep path and is very limited by topography. So almost all models do really well on it, honestly.
There's a question from Antonio.
Yes.
Yeah, I understand well the concept of lava lobe. It's a unit of lava, like a something like this, like a pahohoeto, or what is it exactly?
In a way, but it's really kind of a volume of lava. It's not physically a lobe. It's called a lobe because it's an ellipse, but it's not a lobe in the sense that it has a crust and it breaks out. It just, instead of transmitting kind of squares like in Mr. Lava-Loba, you're transmitting ellipses.
Okay, thank you.
Oh, cool. Here's trying to run Mr. Lava-Loba for Faguadasville, just putting some nominal parameters. We saw that map before, and this is on that topography, and it did fairly well, just getting the extent right. So Mr. Lava-Loba exists also in Victor, and I wanted you guys to try and run it. So there's an activity that is very, very similar to what we just did with molasses, so you guys can go into Victor and set it up with the setup menu, and then run that notebook. Oops. Oh, I'm gonna give it another 10 minutes again to try that. I'm gonna And you'll see in the notebook that we have quite a bit of explanations of some of the parameters that go in. The run name, the event.
Yeah, when you reach cell number 8, let the code run before you move to the output. It's going to take a few minutes to run, actually.
Yeah.
I'm only at 5% for the moment, so. I'm only at 5% run, so
right.
It actually takes a little bit of time.
Depending on the resolution and volume, it can take, some take only 30 seconds, but some can take, 5 to 10 minutes.
Yeah. Okay, so I see here you put a volume of 36 million cubic meters. So, yeah, maybe we should have taken a smaller volume so
Yeah.
it could run a little bit faster.
Well, we can also let it run and then come back to it after we talk about some of the next models.
Sure.
Is everybody at the point where the model is slowly running its way?
Yeah, mine's running.
Okay. All right.
I don't know if mine is running.
Are you seeing a sort of a, you see how here I have a progress bar where it goes, tell me how much % it's making progress? If you get to that line that says subprocess.run.
I started from the beginning, but I don't see that.
Did you click through the different steps?
Yeah, yes.
Okay. So which cell are you on now?
I'm now just after the cell of the DM. Before the model output, but nothing appears.
Okay. Do you want to share the screen and can tell and see?
Yeah. How can I share my screen here? Oh no. So.
And I can stop mine, and maybe you can.
Yes, I'm now sharing mine, I think.
Yeah, we can see your screen.
Yeah, we can see it.
Yeah.
Yeah, Sarah was asking if there's a preferred way to stop the model run. I just stop on that stop symbol up there, the square. Right, so if you scroll back up, then you can. If you scroll back up, then we can see if you're already run some of the previous cells. Doesn't look like it. Right, so if you just stand on one of the cells, the first one to import, and then on that. Yeah, and keep going.
Shall I keep going or not?
That sometimes takes a second, because you see that asterisk is thinking about the DM plot.
Okay,
right?
now.
So that went well, and then it could continue. And now I'm gonna get the sub process, and now that will start showing you that progress bar.
Okay.
Okay. Great.
Okay, not running. Thank you.
Cool. Okay, excellent. So let's go back to the presentation while everybody's model is running. And we can talk about, what was that? Samuel is dialing in. Hold on, looks like something went wrong. Oh, shoot.
Weird, I don't have anybody in the lobby. Can you hear us, Einat? Okay. I think she was disconnected. So let's wait for Einat to come back. Don't hesitate if you have any questions. Hey, you're back.
Yeah, sorry, our internet just crashed. So
Okay.
we're both back now. Sorry about that. All right. So, all right, cool. So the models that we saw so far are very good about fairly quickly giving us a map of flow extent of where the lava would go. But very often, we also want to know how quickly will the lava travel. Say, do you want to evacuate everyone that's downstream because that lava might get there, but what if it only gets there in a week, right? I mean, you can give people an hour or a week to evacuate. That really makes a big difference on their lives. So now we're going to talk about codes that let us answer that question of how quickly will the lava travel. One thing that is very important to know is the rheology or viscosity of the lava. This is a very simple situation where the velocity depends on the density, the gravity, the thickness of the flow square, so it's very sensitive to that, the slope of the ground, and then the viscosity. So if we have a higher density flow, it'll travel faster, and we can get higher or lower density by having more or less bubbles. So that's something that's important to capture sort of as the lava is erupting, so that you can have that there, because even having 50% bubbles is going to make it move twice as fast. And then thickness, that's always very difficult to constrain in the field, but you can get sort of a nominal value for other flows in that area or from other techniques. The ground of the slope, you get the slope of the ground you get from a DEM. So it's important to have something that doesn't have too much errors or spikes or things like that. And then bulk viscosity, that can come from composition, microstructure. Do we have a lot of bubbles? Do we have a lot of particles and crystals? And temperature, of course. So for Newtonian fluid, this velocity relationship holds. And then there's other types of fluids, for example, a Bingham fluid that has a yield stress that has to be overcome before any flow can happen. So then this relationship has the same components again, rho, g, sine, slope, but also has the yield stress come in. Or Herschel-Bulkley, which is a slightly more complicated fluid that may be relevant for magmas and lavas, where you have a yield stress and a power law relationship between stress and strain. So then that parallel relationship comes into these exponents, n, that can be 1 or for Newtonian, or more than 1 or less than 1 for shear thinning and shear thickening fluids. And then Hc is a critical thickness that the lava has to overcome before it can flow. There's multiple codes that are solving these physics-based equations and take into account lava properties, and they vary by kind of the assumptions that they make on uniformity. So for example, there's a class of models that are called depth average. So they assume that there is no vertical motion, and all the velocities are just in the horizontal space. So a one-dimensional code that's popular is PyFlogo, that was initially written in Excel, and then was translated into Python by Oriel Chevrel, and we have that on Victor. VolcFlow, developed by Karim Kalfoun, which we have variations of, but it's definitely a work in progress, because VolcFlow was developed in MATLAB and as a closed application rather than an open source code. So it's a process. Then there's a code called IMEX lava that come from the Italian team of Mattia, and then Lava 2D that was developed in by the USGS recently after the 2018 eruption. So looking at FLOGO is a one-dimensional, along track, deterministic physics-based model. So essentially, what you give it as input is slopes along a track. So if you have a uniform flat surface that is dipping at 30 degrees, then you have a 30, 30, 30, 30, 30 line. If you have something more complicated from a natural situation, then that would come into basically a CSV file of slopes. You also have to give it an initial channel width and flow thickness, initial temperature, crystallinity, and composition. And then it follows the lava along that line and looks at the evolution of velocity, width, thickness, crystallinity, viscosity, and temperature. And then spits out all of these along flow parameters, as well as the maximum length that the flow reaches. Once it gets to a velocity that is less than a threshold, so very, very slow, then it says, okay, I'm stopping here. FLOGO is often tested against field data of velocities, temperatures, and channel width. For example, for these 3 test cases in Hawaii and Reunion. And can judge about how successful it was. And we have FLOGO, and you're welcome to try and use it. I didn't include a example here, but we can go and look at shared models, and his PyFLOGO here, and there's a lot of examples. There's a way to run it, and this is the source code itself if you want to look at it, or if you want to change it, for example, for different conditions. For example, the project we did at Lamont was changed PyFLOGO to have to also include an evolution of the bubbles rather than have it constant throughout the flow. And there's a PyFLOGO notebook that you can go in and take a look at, and has a kind of same component that you'll see in all the other notebooks, and it spits out the results of temperature, viscosity, width, crystallinity, all these different parameters that come kind of along the flow evolution. And of course, in a notebook, you can also control what output you want to see. VoltFlow is a 2-dimensional depth average model that solves these equations of conservations of mass and momentum, and disperses the lava on a topography. And there's different variations of it, some that are more applicable for lava with temperature solvers, some that are more applicable to debris flows and have different parameters, right? For debris flows, you have things like cohesion, and for lava, we'll have parameters such as viscosity. IMAX lava solves a similar set of equations. This is a conservation of mass equation, and here are conservation of momentum and also energy. So we have a solver for the temperature as it goes in, and then that feeds back into the viscosity as well. So IMAX lava, we have on Victor, this is the same test case from Pico de Fuego eruption that we saw earlier for downflow, but because this is a physics-based kind of evolution model, then instead of just showing what is the model extent, now we can show a time series. So here's after a few hours, This is just the flow starting here, and then it's dispersing, and that's the extent after several hours. And you can see also it gives us the flow temperature, not just kind of probability of getting there. So, for example, if you're trying to assess the impact on infrastructure, remember that lava flow that cut that hot water line. It's important to know what would that temperature of the lava be once it gets, a few kilometers away from the vent, and how it could impact the infrastructure. These are sensitivities to different parameters. So there's a lot of different things that you can control in IMAX. It's things like the yield stress or the reference viscosity, the resolution of the grid matters quite a bit. And here's the temperature dependent of the viscosity. Here we tried to run IMAX for an Idaho National Lab in the Snake River Plain. So we just had a vent close to where a recent vent has been. And you can see, again, a time evolution. So this is 1 day of flow. This is 1 week of flow, 2 weeks of flow, and so on. So I wanted to do an activity where you would also run IMAX lava on Victor. But first, to do that, of course, we want to see how is everybody doing on their Mr. Lava Loba runs. Mine is at 70%.
So mine finished running, but then when I tried to run the model, I got some name errors about the step.zfill. It says that step isn't defined, like the name step.
Yeah, I got this too, and I think you got to change.
Well, step get defined at this line here. You see step equals 1. So you need to make sure that you run that line first before you do step.zfill.
Yeah, so we have to change the run number by step, right? Is that correct? In cell 13, that's the one?
Yeah, it looks like in the code that we open up, it's instead of it being step equals 1, it's run _ num equals 1. So I think that might be what fixes it then.
Yeah, you might be.
Okay, so what are you saying?
So I think if you change the run _ num by step,
yeah, I think it is.
And then you run it again, I think that should work. Let me check that. File name, no file name is defined. Okay. Source file name. Okay.
I think it needs both.
Right.
Changing that.
I
don't remember changing that.
I know, I'm looking at the...
I'll fix that after this.
Yeah, I mean, I see that in the workflow that it's wrong, right?
It's wrong.
Okay, so what should I do to fix it? And the run name.
Name.
Change the run name.
Can you put in the code? What in the chat? What? Thanks. So, I mean, step needs to be a number, and then the run name. It's usually defined at the top, right? So run name should have been defined at the beginning. So you can make sure that that is defined.
Run name. Oh, okay.
Should just be this. Oh wait, it's run num. It's my bad. It's that first one was wrong. I need to work on my variable naming.
Yes.
So I went in and changed it to what yours looks like on your screen that you're sharing, and tried to run it, and now I'm getting like a whole bunch of new errors.
Oh.
It's this one. It's like it's the.
Do you want to share your screen so we can see what the errors are?
Yeah.
Yeah, I'm also getting some errors too.
Oh.
So what I changed is up here, I changed it to step equals 1, and then step here, and then down here, this used to be the run_num, and I changed that to step.
Yeah.
And then I tried to run this, and then this is what came up.
Oh goodness. Let's see. Go to the bottom. Right. It just doesn't. I mean, it's the one error that it's not seeing the file name. So if you.
So I think it should be 0 in this case. That step equals 0.
Okay. Try that. There you go.
Okay, awesome.
Yay.
Can you show me again your so
Oh,
what did
sorry.
you change? So you change the step, and then so step equals 0, right?
Yeah, and that was that, right? You didn't have to change the next lines.
Yeah,
Okay.
I can. Yeah, I'll send a copy of the text.
Okay, thanks.
Yeah.
And that's just for those first two after model output. I didn't change anything in the like fig chunk.
Okay.
Right.
Thanks. Yeah.
Are other people's models still running?
Something.
And we can talk about the output already, since hopefully everybody's going to get the same output. But what's cool that we have here have multiple sources, and it was able to distribute it. And this is give us the thickness of the residuals, but because that's the file that I asked it to give me, but I can also ask it to give other outputs. So we can get thickness, and you can get temperature, depending on what you asked it to output. %, almost there.
I have finished, but I have error in the output.
Okay. Did you make that change that we just said?
Yeah.
Taking
Yes.
equals 0 and okay. Do you want to show us what the error is? And so if you scroll down, then we'll see if it's about not finding the file. Yeah, so yeah, so Melida also has that error of not finding the file. Can you scroll further?
If you scroll all the way down.
Yeah, so it's not finding the file. If you go into your folder names, it's the folder, and see what names you see.
This is the folder name.
Drag that right side.
Yeah, just like make that side, left side a little wider by dragging that boundary, so that we can see the files you have in your name, the names of the files you have there. Yep. So it has number 1. Right. Try making step number 1. And then running this line and the next 2. Cool.
Okay. Thanks.
Awesome. I literally want to try and see if that works for you too. So we apologize for some of the errors in the workflows, but this also shows you how to address some of the errors that you might encounter. So for example, if it's giving you an error that is not finding a file, a first good step to do is to look whether that file name exists, or are we kind of, if it exists the way we expect it to be, and if the names match, and where that mismatch might happen. Okay, so like I said, IMAX, I have instructions here, and you're going to see that in the slides. I'm going to fix that. But the idea is to run the same workflow that comes with the IMAX distribution and see the map. But IMAX, because it's a kind of a physics-based model, it's a little slower, and that wouldn't be something that maybe make a lot of sense to do right now. But I think I recommend that you do it after class or in your time, and it gives really beautiful results. All right, so the kind of the most complicated class of models that we can have is the computational fluid dynamics of CFD models, and these are models that solve the differential equations of continuity and conservations using different mathematical techniques. For example, finite elements or finite volumes are techniques to solve these equations, and they're very good for when you have a complex geometry and complex rheology and distributions, and you want to capture all that complexity. There's many general CFD packages out there that are used for anything from engineering to biomedical, simulating blood flow in veins and industrial fluids in a factory, that we can use for lava flow and have been used. The same for finite volumes. There's Flow 3D. There's Open Foam. There's a Magma Foam code that uses an Open Foam package as a basis, and then adds to that the relevant equations for magma and lava distributions. GetFEM is a kind of a generic finite element package that, for example, in our group, we used as the basis to simulate flow solidification and breakout. And there's particle hydrodynamics code like GPU SPH or lava SPH that you can also get. These are a lot heavier lift computationally, but they're still doable, and they are very good if you want to look at things that are kind of small scale process focused. I wouldn't necessarily go and model an entire flow field with finite elements, for example. Last thing I wanted to talk about after seeing all these different models is how do we assess models and model outputs? And two important ways we do that. One is benchmarking, which includes comparing the performance of a model to a specific case with a known solution. So that can be, for example, an analytical solution of how fast a flow should advance on a slope, for instance, or experimental results from the lab where you know this is how it behaves in nature, or in like in reality, like for example, a lot of taste models get benchmarked against wax or syrup flows on slopes. Another is to compare models to each other. So you can run two models and see how their performance differ. And by performance, I mean how their output differ, but also how much one was maybe more expensive computationally than the other, or one is, and you do that when you don't know the solution, the true solution. For example, when you're trying to do a forecast and the flow hasn't happened yet. So you don't know if your model is doing great or not because the flow hasn't happened yet. But if you have 5 different models and you can see some give you a fairly similar result and some give you something that's very, very different, then maybe that one's right, but there's less likelihood for that. So that's another way that we're thinking about assessing models. An example for benchmarking is, for example, an analytical solution. In this case, it's for a dam break scenario where you have all your liquid contained in kind of a reservoir on one side of a channel, and then you take out a wall and the flow flows down the channel. And there's an analytical solution for that. And then you can compare whether your model is solving it correctly or not. There's the other end of the spectrum is comparing with natural flow examples. And one of the ways to quantify that is looking at the flow footprint and then comparing where the model field A and the natural field B, whether they the area that they intersect compared to the area that is the combined footprint of all of them. This is called the Jacquard Similarity Index. And there's pros and cons to using that, but it's a very popular and a quick way to compare footprints of flow models versus reality. Another kind of quantity to compare is the flow branching index. So a low branching index would be a flow that is just the one line and everything is on the one line. And a high branching index would be a flow that has a lot of different paths going all over. So if you have a model, you can calculate what your branching index is and then compare that to the branching index of the natural flow. Here's a kind of a comparable value called the braiding index that was calculated all along the channel of the Mauna Loa 1984 flow in Hawaii. So you can see that in some places it's high, some places it's low, depending a lot of times on slopes and obstacles, and then comparing it with that can be another quantity to compare with your flow models. So there's a an effort a few years ago to define a kind of a hierarchy of benchmarks. Some that are very simple that we expect all lava flow models should be able to solve. So for example, that would be that dam break scenario. And here is some of the results for different models like bulk flow and flow 3D and open foam. And the true solution is that black line. And you see that bulk flow did very well. Some of the others didn't do very well on the kind of early phases, but then they converged kind of at the later times. Something that's very relevant situation for lava flows and volcanic eruptions is where you have a slope and you have a source with a known flux. So we have an analytical solution for that, so that the distance as a function of time depends on density, gravity, flux, slope, and viscosity, of course, time. And this is the distance and the flow thickness. And there's an analytical and an experimental solution for that, and we compare that with a few different codes, and they mostly did okay. We also included molasses here, but remember, molasses doesn't solve for time; it only solves for distribution. So it was able to match the furthest distance correctly, but for that we had to kind of give it the volume and thickness, which is something you don't always know in advance. Here's a benchmark 2 performance for IMAX lava and IMAX lava performances on different benchmarks. Benchmark 1, benchmark 2, and benchmark 3, which is a spreading axisymmetric cooling and lobe or dome, really. And it was able to solve that because, remember, IMAX lava solved for temperature and velocity over time. This is the experiment that the benchmark 3 was based on, where there was an injection of silicone oil that's hot, and then viewed from above, its extent, kind of a radius over time and temperature over time. So this is how different models were able to replicate that data from the experiments. And you can see that most of them did pretty well. Benchmark 4 that we defined in that paper was based on an experiment at the Syracuse lava facility, where we poured lava on a slope that was smooth and was all sand and a known constant slope. And then there was an obstacle placed in the middle of it. So what we were trying to test the models over was distance over time, but also the thickening that happened behind that obstacle. So as a function of the angle. So if it was a kind of a sharp triangle or a wider triangle. And the black lines are the experiment, the dots are the experiments, and you can see that there was already some variation in what the different models predicted, even though the overall length and time was fairly similar. But this is something that's important to know and to say, okay, if I'm planning a barrier to divert the flow in Iceland or La Palma or anywhere, or if I have a building that's set up, will it be overtopped, and when will it be overtopped? And the different models have different opinions on that. So it's something that is important to know, whether you want to shoot for something in the middle or always want to do the worst case scenario and things like that. Again, model intercomparison of different models. This is already including, this is what we had in the paper, but that's adding Q lava and Mr. Lava Loba for the flow at Etna and looking at the Jacquard index and other fitness indexes. One thing that's, again, important to know is that some of the stochastic models are very good at matching footprints. Like this is molasses for Cumbre Vieja. And then more the physics-based, like bulk flow, are better at matching velocities. So this is flow velocity and flow footprint over time using VolcFlow for the same eruption. This is for IMAX, and it's showing flow velocities in meters per second and kind of focusing on that channel, for example. So if you remember, now we have that kind of data that from the field with drone velocimetry, where we can test whether our models are correct also on that kind of finer scale flow speeds. So we have a benchmark workflow on Victor, so I'm going to turn to that now. Yeah. Sorry. So I put that open the wrong folder. Where's my right? So what we have in this notebook is, after you import some of the packages, you can set up inputs that would be common to all the models. So you want to run the models on all on the same DEM, on the same vent, and then have the same kind of runtime and volume and flux. So these are obviously related to each other, and then start running the different models. So in this notebook, we are running Molasses first with its own sort of bookkeeping and parameterization. And then we go on and run Mr. Lavaloba, again, with its own specific parameters. Next is IMAX, getting its own set of parameters, and Lava 2D, and setting up that input file, and then we kind of run step by step. And then eventually, we're not going to run it right now, it's going to take a while, but you get kind of a matrix with the maps from the different, the 4 different codes in this case. And then once we have more codes available, we're going to maybe add them to this intercomparison workflow. And then that's something that we can use. If you, for example, have an expected eruption in Iceland in 2 weeks or in 3 days, and you have an idea of where that vent might open, you want to give kind of an ensemble analysis of what different models predict for that situation. So I think this is what I have for the presentation. I wanted to also share a reference that there's a lot of very useful information in kind of 2 volumes that came out a few years ago now that talk about detecting, modeling, and responding to effusive eruptions by Andy Harris and others. And then this is a special volume of Annals of Geophysics that came out of a special meeting held at INGV. And there's a lot of analysis of like different models and different methods, and as well as the response to eruption crisis. And note that this was before the 2021 eruptions of La Palma and Reykjanes. So that I'm sure there's a lot of updates on that as well. So to summarize, there's many factors that impact where lava would go. There's many models available at varying levels of complexities. And when you come to using any of these models, you need to consider what do I need? What are my needs? What is my goal? And then choose the tools that are appropriate for that. And then it's very important to go through benchmarking and intercomparisons, or at least make sure someone else already did for you, so that your choice of models is informed. And for Victor, we're trying to put these kind of models available in your hands so you can take them and use them when you need. So that is my presentation, and I'm gonna stop sharing now and we can have a discussion, questions. Happy to take any questions on that.
Yeah, there's a question from Mickey in the chat. She's not finding the DEM. Actually, the name of the DEM should be different.
Yeah.
It should be called Mauna Loa. Let me see. Mauna Loa 30 meter UTM 55N.ASC. Not sure why you have Mauna Loa 000.
Right. Maybe you want to share that.
Oh no, sorry. Sorry, that's at the end. So okay, sorry. I thought it was a DM, but no. Okay, you got that after you run the model. Okay. So I'm not at that point yet. Maybe Sam can answer that. It seems to be something related to one of the output file that you get in the end.
Did it already run the model, and are you seeing outputs?
I'm not totally sure. I think so.
It's .asc or ASCII files, but if you want to share your screen, that
because
it's easiest to visualize one.
Yeah, you don't want to think abstractly about what my code is. Okay, so this is the error I get at the end when I try to run.
Right. So if you go up, did you actually? Because I don't see any output files there. So if you go up a little bit and see whether your model actually ran. It says complete process.
Can you take out that last part with the std out equals subprocess? Just take out that last part.
This?
Oh yeah, from there to the end. And then rerun.
The comma, yep. I'm gonna spit out a lot of outputs, but
it worked either way. So
right. So now you're already seeing output files. So I think it was just go and run.
Okay.
Yeah, that's why I usually stop the output from happening, because it just spits every time step out and shows you some data.
Yeah, it did run fine on mine. I actually got the figure in the end. Yeah.
Okay, so maybe mine just didn't run and I thought it did, so that might have just been my issue.
That's fine.
Thank you.
Awesome. All right, great.
I have another question if we have time.
Yes. Mm-hmm.
For all of these models, when using a DEM, are there any considerations for DEM resolution or extent or things to take into account to make the model run well?
Some of it has to do with the availability of the DEM. So sometimes all you have is a kind of a 30-meter DEM from SRTM or Copernicus. A lot of times you have access to a very high-resolution DEM, but you might not need it. I find that it has to do a lot with the general slope, right? So if you have a very high-resolution DEM, but the overall slope is very steep, so it's not going to matter as much. While if you have an area that's very flat, like in Reykjanes or in Hawaii, then every kind of building or ditch can divert your flow, because your flows are also very low viscosity and they're thin. So then you want to have something that is a higher resolution to capture that.
Okay, so it's kind of a case-on-case basis.
A little bit. I mean, sometimes if you want to get a general sense of how things are going to go, you can maybe get a lower resolution one, just to get an overall map, and then start digging more into what you're looking at. Obviously, if you have a higher resolution DEM, your model is going to run more slowly. So if you're trying to do something like probabilistic assessment, then and run 5,000 models, then it's going to be a little tricky to do on a 2-meter DEM unless you have a lot of computing power. I mean, you might want to do that once, because if you're trying to do like a hazard map, that's something you do every, I don't know, few years, then fine, it's okay to run lots of high-res calculations, spend a month of calculations, but that's not something you do during an eruption, for instance.
Okay, thank you.
Yeah, it also depends on your area of interest. So, for example, if your area of interest is very big, if you want to, look at inundation on the site, and you want an area that is like, let's say like 50 kilometers by 50 kilometers, you definitely don't want to use a 5-meter DEM for that.
Yeah.
So it's gonna run forever. So you can also scale your DEM resolution based on what is your area of interest and go from there.
Right.
Yeah, I think ideally in the long term we'll have, like Titan does adaptive mesh rendering. So, in the long term we'll have models that you can scale up or down depending on your point of interest or area of interest.
Right. And there's kind of some tricks, like IMAX only looks at the part of the DEM, and you can tell it to look at just some of it rather than the whole thing.
Yep. Yeah, there's some models also that run in parallel that you can actually assign a box that is just a fraction of your DEM and say, okay, each node is going to focus on the simulation on each of these part of your total area of interest.
Right.
I mean, these are more complex to run, but yeah, that can be done.
Okay, thank you.
Good question.
Yep. Any other question?
Yeah, I have another question. It may be a silly one, but could these models could be applied in cases of submarine volcanism if we had the bathymetry DEM? Even if there is the limitation of water that acts like a brake to the lava, but to which extent could be applied in submarine volcanism?
Yeah. So the answer is yes, for sure. Depending on the model, you might or might not need to adjust some of the parameters. I mean, if it's something that doesn't care about the physics and you just spread the volume you have, like molasses, it doesn't really care, right? You can just disperse it. You might give it a different thickness or things like that, if you know what you should expect. But models that solve for cooling and include density and pressure, then you just need to adjust some of those parameters. That might not be super accurate, but it will give you a general sense. If you want to dig more into the models and convert them into submarine, that is doable. Like, for example, PyFlogo was just adjusted for Venus with this thicker, hotter atmosphere, and they just needed to add a couple more parameters to the code, and it was able to do that. And the code that we developed here that is based on finite elements and solve for solidification, it has a way to add in different cooling rates at the surface to include kind of a cooling in a submarine environment.
Okay, thank you.
I will add on, if you know of anyone working on submarine volcanic codes or even something adjacent to those, we'd be happy to look into it and add it to the platform or work with people to convert something.
Like, I know people who looked at submarine lava flows and just use downflow and just said, it's going to go down. It doesn't matter as much when the water is there. I mean, the cooling will be faster, so maybe you want to kind of limit your length or things like that. But it doesn't matter as much for some of those more kind of probabilistic codes.
All right.
Right.
Well, time's
So,
up. If you have any other questions, don't hesitate to ask either by email or via the chat on Teams. So anyway, yeah, we'll be happy to answer them. Thanks. Let's meet next week. Okay.
Yep. Thanks, everybody.
Thank you.
Thanks, Einat. That was great. And yeah, have a good rest of your week and see you next week, guys. Bye.
Thank you. Bye.